I am recording. I am letting everyone know that they are being recorded.
You do not have my permission.
I don't need your permission. All right, here we go. Component identification. You want to make sure that you are writing some of this down because it's basically broken down into easier to read format than what PLTW would have given you, but it's the same thing. So we're going to first start talking about resistors. Okay, and the resistor is an electronic component that resists the flow of electrical current. We already kind of know that that's what resistance is. So a resistor is just the component that provides the resistance. Okay, typically used to control the current. So you want to make sure that you have that in your notes at some point, but we've talked about that a few times. So make sure that you understand a resistor controls the current. Measured in ohms, named after George Ohm. And we talked about what Ohm's law is. So this is all recap. We already kind of know what that means. All right. So carbon is an insulator. So it restricts the current flowing through it. Less carbon allows more electrons to flow. You can't see my mouse. Boom. Okay, so the less carbon that you have, the more electrons are going to flow through. More current you're going to have, right? So if you have more carbon, that means you're going to get less flow of electrons. This is a PowerPoint that was redesigned to make it easier to understand. So they're going to use those cats and mice again, so that you guys can kind of understand what's going on. Okay, how does it all work? This is a picture of a resistor right here. All right, so you have electron flow that's going to be going through, and then you have your resistance, the cat, trying to restrict the number of mice that are getting through, right? And then the amount that gets through per second is going to be your amperage. Okay. So that's what they're trying to say. This is the same scenario we kind of looked at before on how resistance and voltage and current all kind of work together. Carbon? I wouldn't call it sand, but it is a material. Yeah, I mean, I don't think it's really sand. Okay, so the different types of packages that you can get in resistors are going to be carbon film resistors. That's the first one, and this is the symbol for it. You'll have variable resistors. This is your symbol for variable resistors. They're also called potentiometers. Basically, you turn a dial and that increases or decreases the amount of resistance that they produce. And we'll show you how that works in just a minute. But this is the symbol for it. So you're going to want to make sure you have that down so you know that that is the symbol for a potentiometer. That is a symbol for a carbon film resistor, which is what we use 90% of the time in the class. Here's another carbon film resistors. These are a 5-band carbon film. These are a 4-band carbon film. The ones in your kit look like they might be 5-band, but they're definitely different in how they are designated. And then the ones we use here in class are going to be a 4-band all the time. And then you have something called a surface mount resistor that gets soldered to a board that sits on the top. Those are 4 different types of resistors. These are the ones we use 90% of the time. So, however, with our component identification lab, it's going to be kind of interesting because those that are here will get resistors from here, and those that are at home will get resistors from their kit. Everybody have that? That's 4 different types of resistors. Carbon film 4-band, carbon film 5-band, variable resistors or potentiometers, and surface mounts. These are really, really small, these surface mounts. Find them on your phone all the time, or electronics devices like that. Those are the resistors that they'll use, really small. Okay, so here's a size comparison. You don't need to write any of this down, just kind of understand. Here's a dime, and the size of the surface mounts are super small in comparison. And then as you get bigger and bigger and bigger, or difference of how much current they can handle, they get larger. So you may have more carbon in this one than you might in these others. Most of the time we use like these light green ones, but they're brown, or these brown ones, tan ones, I guess they're tan. Okay. I did it again. The screen just went black. Okay. Fixed resistors. So the carbon composition, or the element that's made, it's made of finely crushed carbon, and that's this gray area right here. Okay, and it kind of is filled into the resistor, and then you have a coating that goes around it to hold it all in there. And then dependent on how much carbon is actually in here will depend on what your value for that resistor is. And that's a fixed resistor, which is mainly what we use, fixed resistors. But this is where the electric, the piece of metal that goes inside, and then basically the current has to go from here to the other side of that resistor. All right. Variable resistor, or potentiometer. It's just fun to say the word potentiometer. That's why I keep saying it. Potentiometer. Anyway, this is how it's designed. All these little like wafers or pieces are all different values of carbon. And what it is, you can't really tell, but from here you have a point that is going to get connected to a wire coming out. So that's this point right here. And then this dial right here gets turned, and as it gets turned around this circle, it's going to increase the amount of carbon that goes between this point right here, the end of this, and here. So what that means is that depending on how far this dial, or this dial, it's the same thing, is to the right, that's going to increase your resistance. And if you bring it back closer to here, it's going to decrease your resistance. And that's how a potentiometer works. No, I'm just showing you, just so you understand that. No, they're not. They're small. You can get them really, really, really small. Yeah, most of the time when you see them, they will look like this blue.
Oh, okay.
So that's usually what they look like. All right. Other types of resistors. We have a resistor in layout in PCB, which is a printed circuit board. So if you don't want to add a resistor to your circuit, you can print it out kind of like this. And so what you should be able to see is that it would take a lot longer time for it to go through each one of these bands before it reaches to this point. So that would slow it down versus just going straight across. That's one way to make a resistor, or to make it take longer.
Resistor has like a lot of stuff going through it. We try to draw this one though.
Okay. No, you don't need to draw, I'm just showing you. We have aluminum power resistors. These will accept a lot more power or amperage to go through them. These are like, this is an aluminum casing on the outside of the resistor so that it gets rid of the heat and allows it to keep working. And then you have these that are load resistors, which are much, much larger than this type of thing. This is probably somewhere around the area of a foot long, something like that. Those are much bigger than these other types. All right, in DE class, which is this class, yep, we will mostly use fixed carbon resistors. So what we need to know is we need to determine a resistor's value. Like, we need to know how to do that. So there's two different values that we need to know about. One is the face value, and the other is the measured value. In your lab that you're about to do, we're going to be determining face value versus measured value and how close these two numbers are going to be. Okay, so face value is the value that is represented by the color scheme on the actual resistor. So whatever these color bands that are all throughout the resistor are going to tell you a specific amount that's the value of that resistor, or that should be the value of that resistor. Okay, so this is what it should be. The measured value is going to be taken by a multimeter, and you're going to find out what the actual value is. So you can kind of compare what it should be to what it actually is. Yeah, you should write those two down so you know.
Okay.
And we're going to talk about multimeters soon, very soon. Multimeters. We've already kind of covered some of that, so yeah, you're just going to start using them a lot more.
I realized that my wall has more power than my portable pocket charger.
Your wall?
Yeah.
Hmm.
So I'll put the board up, my light was brighter than it was in my power pack.
Interesting. That's interesting. All right. Does everybody have that? And I need to make sure you guys are taking good notes. That doesn't have to be word for word, but you need to have all these things in it. You should be. Do what? You're allowed to. Leave room as we're going through it, you know. You can always go back to the video that I'm recording or go back to the PowerPoint, just go through it. It's up to you. I'm just kind of trying to help you get what we're doing before we move into the real lab. So, how can you tell them apart? Fixed resistors look very much alike. A lot of the resistors look the same. So, the way you're going to be able to tell them apart is they're going to have a color-coded bands on them that tell you what that value should be. Okay? And this is what you're going to want to write down. So I would draw that image right there of the resistor, and so you can kind of see how this is going to, how you're going to be able to tell what value each resistor is. You have a first digit, a second digit, and a third digit, okay? And then you have a tolerance at the end. Your ones at home, I think, are 5 band. I'm going to grab my kit real fast just to make sure. But I think the kits at home is 5 band.
Well, did you say we're right on the color code? Okay. Oh, my head. What does the number mean? The number again?
What?
What does the number mean again? Like numbers, right, 1 to 9?
Those are numbers.
Okay,
They're just numbers. I'm going to explain it to you right now.
I thought you were explaining it.
No. Okay, so looking at your kit, they're all 5 band. Well, no, these look like 4. No, they're 5. They're 5 band. So they're going to be done pretty much the same way, that there's going to be that 4th band that we're not, or that 5th band that we're not really going to use. Yes.
What do the bands mean?
Oh, that's what I'm going to go over with you right now, so everybody understands. Okay, so the bands have, you have 3 or 4 different bands in this, on this resistor, right? So you have the first band, which is going to have a color, and this is going to be the first digit of the value of that resistor. So in this case, it's orange. So yeah, you would look at orange, and orange is 3. So the first number is 3. Then the second digit is the second color, and that's going to be white in this case. So we go down here and we find white, which is 9. So right now we have 3, 9. And then the third digit is how many zeros after that, after those 2 numbers that you have. So in this case, you have green, so that's 5. So you'll have 3, 9, and then 5 zeros. So it'll be 390, 0, 0, 0, 0. And that's the size of that resistor. Okay. Which is I think it's 3.9 mega, but we'll go over it right now. The last band is going to be one of 3 colors. It's either going to be clear and it has no color, it'll be silver or gray, however you want to look at that, and that'll be 10%, or it'll be gold and that'll be 5%. And that's your tolerance. And I'm going to go over what tolerance is with you right now in a second. How much can I tolerate you, huh? So one of the issues with electronics is that the components keep getting smaller and my eyes keep getting worse. So I have to use a cool magnifying glass to actually see the colors. Yeah. So no, I have a bunch of them. I'm not the only one with bad eyes. Ah, maybe these are 4 band.
I told you.
It just looks like there's a band that runs right next to the right next to the end of the resistor that is not an actual band. Like that looks like brown, 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 brown. It should be red. Oh, that is red. Never mind. Red, black, brown. Red, black, brown would be red. That'd be 2, 0, 0. 200. 2, 0. You just have to have really good eyes, and you can't assume that that is a number. Red, black, black, brown. No, that's a 5. That's 5. Red, black, black, brown would be red would be 2, 0, 0, and 1, 0, which would be 2K, which is what that is. Yeah, 2K. Oh yeah. This is brown, brown. It must be black, black. I must be looking at backwards. Brown, black, brown, brown, black, brown, black. Interesting. Okay. But for the class, you're gonna be working with using 4 bands, not 5 bands. I know that the resistors we're going to be using in the class are going to be 5 band because that's what we have for the house, for your house. But for the most part, when you're here, we're going to be using 4 bands. So, and on the tests and quizzes, we're going to be dealing with 4 band. And I'll just kind of try to explain what you're using in the 5 band. Okay, so hopefully you got all that written down, all the different colors. What? What? Okay. There's some acronyms that we'll go over. I think the one that the kids liked the most was, I don't remember what the first one. Never mind. I'll tell you in a minute. I can't remember what the first acronym was. Maybe Betty Brown runs over your garden, but Violet Gray won't. Something like that. Tolerance is next. How do you know that? Oh, you're so magic. That's cool. All right, tolerance is the last band. You'll never get a resistor that has the exact the color codes indicate. It just doesn't happen that way. You go further and further down. It's super difficult to find a tolerance that is exactly 100% or 0%. So what they do is they get it as close as they can, and the quality of that resistor will be given a tolerance value. So if it's within 5% up, above or below the value it should be, it's going to get a gold. If it's 10% above or below the value, it's going to get a silver. And if there's no band on that at all, then you're looking at a 20%, which is not a very good resistor. Usually, though, the higher the tolerance, the cheaper the resistor, because it won't be perfect. Yeah, I would write down what they mean. So a 100 ohm resistor with a gold band means that it's going to be up or down 5%. 5% of 1,000 is 50. So it can go up or down 50 ohms. So if it's supposed to be a 1,000 ohm resistor, it can be 1,050 or it can be 950, depending. All right. So there's a couple of mnemonics that they're going to talk about. This is the one that I think is the best one. Bad Betty runs over your garden, but Violet Gray won't. So you can remember the color code pattern so that you can remember what values are each color, because you'll have to know that. No, not when we get to the final test. You're going to have to know how to do it. So that's the best one. Honestly, there's some other ones in here, but they're a little bit sketchy. Or you can remember that it's black, brown, and then the colors of the rainbow, and then gray, white. It's up to you how you want to remember that, but that's what it is. It's black, brown, then red, orange, yellow, green, blue, purple, or blue, violet, since there's no purple, and then gray, white. So it's up to you guys how you want to remember that, but this particular one seems to be the best. Bad Betty runs over your garden, but Violet Gray won't.
Violet Gray won't. Violet.
Violet?
Yeah.
I think it's a character from a cartoon that my son watches. Yeah, that's it. See, you knew. You know who Violet is.
I said Violet is bad.
That's the best one. I'm not. The rest of them are just not something you would remember.
Better bet ready or big. Oh gosh.
Yeah, exactly. It's too hard to remember that. All right. So we're just going to move on to this one. We're going to start with an example. Looking at this particular resistor, we have a brown, black, red, gold. So the first band is going to be brown, so we'll go to brown, which is 1. Second band is black, so that's a 0, so it's 1, 0. And then you have your multiplier red, which is 2, so you'll have 2 zeros after that. Check in that little triangle thing right there. I think I had one last week sitting in there.
You were right.
I know. Huh? It's not in there.
Might be some good stuff too. Wait, so you need to write this whole thing down? You just need to write down the colors and then write down that's like
All right, so brown, black, red, gold. So brown is 1. Okay, black is 0. And then we have a multiplier, or how many zeros we have, which is 2 zeros after that. So that's 1,000 ohms. Okay, and then your tolerance is going to be 5%. So it'll be plus or minus 5%.
Where do they get the 10 from though? The 10 times 100 ohms? Without the 100 ohms?
What are you talking about?
Like, they give you the solution.
Oh, yeah, because you're already going too far. Because you're multiplying by 100, when all you really need to do is add the number of zeros, which is 2 zeros at the end. You can multiply it times 100 if you want. 10 times 100 is still 1,000.
Yeah.
So
it's either 1,050 or 950.
Exactly. And the way that, but they'll tell you that this is how your solution will end up being. It'll be 1K or 1,000 ohms, 1 kilo ohm plus or minus 5%. You don't necessarily have to figure it every time. Yeah, it's a simple calculator though, not like a nice calculator. It'll add, subtract, multiply, and divide.
Oh, yeah, good time. Yeah.
All right, so that's example 1. Example number 2, here we have orange, yet white, green, gold. So we have orange, which is a 3, white, which is a 9, 5 is green. So this is the same thing we did earlier. 1, 2, 3, 4, 5.
I think it's 5 nines, though.
5 zeros. It's the number of zeros.
Oh,
All right.
okay. And then yellow.
So then, and then you have gold, which is 5%, right?
We got 10K. We want 1K.
So then you're going to have to figure this out in SI notation. So you do your engineering notation. If your decimal point's there, then you'll move it in groups of 3.
3.5.
So then it should be 3.9 times 10 to the 6. Okay, and then you figure out that this in SI notation is, nobody knows?
Oh.
It's all right, it's mega.
Wait. Let me look at my book.
All right.
Okay. 10, yeah, mega.
Yes, mega ohms plus or minus 5%.
I put plus minus 5.
Huh?
I put plus and minus.
You put plus or minus because it can go up or it can go down 5%.
I still need my 5 though.
Yeah, and so that would be your answer. Okay, and then they give you the answer, or they break it down for you in the notebook, so you can see. But it's the same thing, 3.9 mega ohms at plus or minus 5%. Okay, and that's pretty much how you're going to figure out resistor values. This one gives you the value, and they want you to figure out what the color code is. 15 K ohms. So 15 times 10 to the third. This one you need to go ahead and change it from SI notation into regular notation before you do anything. So, well, you convert it back. So instead of it being 1.5 K, you convert that to 1.5 times 10 to the third. Then you figure that out and you should be able to keep going. So then you move your decimal place over 3. So you should end up with 1500.
So it's brown, green, red, gold.
Yes, that's correct. So then you get your first color is the 1, which is brown, right? Second number is a 5. So we go to 5. And then how many zeros? 2.
2.
So we'll go to the red. So it should be brown, green, red. And then your tolerance is 5%, which is gold. So brown, green, red, gold. That make sense?
We have a lot.
What?
We have a lot more.
We have to do capacitors. Okay, so I'm gonna move on so you guys can see that, but brown, green, red, gold is the right number. Okay. Using a digital multimeter to measure resistance. We're not going to do this next part, which is a lab. They want, or not a lab, but an experiment where you color in using a carbon pencil and then measure the resistance between the 2 points. Yeah, we're not doing that. This is going to be part of your lab, so we're going to skip that. And then obviously we'll have a quiz later, but not right now. What is inserted here and in CPS? That's weird. All right, so now we're going to talk about capacitors. Yes? It'll be later on. Yeah, it won't be today. So you can cheat. It'll be an open notes quiz anyway. I can't give you anything but right now.
Is this a new page?
What's that? This is still part of.
This is a new page.
This is still part of component identification, but you can call it a new page if you want. So if you call the last one resistors, you can call this one capacitors, and that's fine.
So we do use a new page, or do we write it?
Sure.
Show sure is not an answer. Is that a smiley face? Okay.
What? All right, capacitors. So first thing before we get into what a capacitor is, we need to explain how a battery works. So you don't have to write this down. This is just information. Chemical reaction formed in a cell, which is why these are called cells, sometimes battery cell. This is a chemical that's inside here that is reacting with another chemical in order to produce electricity. Okay, this is a slow but constant discharge, so it's going to be the same value for a long time, but it's going to eventually run out of power. Okay, kind of like, not an old person, like a turtle. They're slow. All right, I don't know why. So, it's same thing, just different kind of chemical. Battery is essentially a can full of chemicals that produce electrons. So it's an electrochemical reaction. So somewhere in your notes, just kind of write down battery is an electrochemical reaction, so you understand that that's going to be different than what we're talking about. But that's how it works. And inside the battery, there's a chemical that's reacting with the zinc inside it, or the carbon rod, however you want to look at that. And then those particular materials, an electricity, an electrochemical reaction that creates electricity. Yes. All right, so how does this work? You have a negative terminal and a positive terminal. You can't see my mouse. You have a negative terminal and a positive terminal. Then what you're going to do is have all of these electrons collect over here at the negative terminal. And if you remember, there's the opposite poles or the opposites attract. So these negative terminals are all trying to get over to this positive terminal, but they can't get there. So they all collect up here at the end of this battery.
Is that why they were pumped up?
Do what?
Is that why they got pumped up?
No, it's just so you know the difference in ends. No. So over on the positive side, you have all these holes waiting for these electrons to jump to. So as of right now, they sit here and wait to fill these holes. So that's where they're going to try to get to. When you connect a circuit or something between the two connections, the negative terminal and the positive terminal, then you're going to allow all those electrons to flow over, and that's where you're going to get your current. Okay, now you have current going through.
Don't they have a wire at the bottom where they go through?
A wire?
Yeah, like.
On a battery?
Yeah.
No. No wires on batteries.
So.
No.
Okay, never mind.
No, that wouldn't make sense. That would be difficult. And so that's how it works. Electrons flow from the battery into the wire and then must travel from the negative to the positive terminal for the chemical reaction to take place. So once that happens, that's why batteries can sit on a shelf for years and still have power, because they're not actually, those electrons are just sitting there until you connect them. As soon as you connect those wires up, then they start moving. Okay, so, but we're not really here to talk about batteries. We're here to talk about capacitors. So, capacitor is an electronic component that can be used to store an electric charge. Now, you should write that down because we haven't really gone over capacitors at all. They're often used in electronic circuits as a temporary energy storage. So basically, they'll store energy for a while, and then as they're needed, they get rid of the charge that they have. Capacitance is measured in farads, and it's named after Michael Faraday. I don't think we've talked about this yet, so you want to write his name down, Michael Faraday. And he's a British chemist who was studying electromagnetism. And you'll find that magnetism and electronics are very similar. I would write down key things. Definition of a capacitor, definitely what the units are, and the person who's named after and what he did. Those are the key things that I would make sure I had in my notes. All right, is everybody good? What do you mean no? You're saying the wrong words. It's like, yes, sir, let's move forward and learn more.
Never.
How it should be done. It's going to be fun. Capacitors are interesting. We don't get into capacitors too much in this class. However, when you go further in electronics, you'll see that capacitors are actually really, really important in almost every electronic device that you have.
I'm ready.
You're ready? Well, then let's move forward. So what is capacitance? Capacitance is a property of an electrical device to be able to store an electric charge. In this case, they're going to say it's like a mighty electrical spring. Wait, so just make sure you have that, what capacitance is. No fancy boing sound. I expected like a cheesy sound effect right there. Boing. I'll make one for you. It is a PowerPoint that took PLTW's information and made it easier to understand.
So they copyright.
No, they took the same information and made it easier to understand. But it's okay. It was made by a PLTW master teacher, so it's cool.
It's like a knockoff.
It's not a knockoff. They work for PLTW. They just rewrote it. All right. So, property of an electrical device to store electric charge. That's what capacitance is. So this is like a water tower. This is their analogy here. So one way to understand a capacitor is to imagine it being a water tower that's hooked up to a pipe. So the water tower is going to store water pressure. Okay, so it's going to store all this water in it. When the water system pumps produce more water than the town needs, then it fills up this water tower, right? Then as the town needs more water, then it can release that water later as the town needs it. And that's basically what it does.
Is that how the water? Oh, wow.
Water towers work, yes.
Yeah.
Yes. That way you don't have no water pressure when you wake up in the morning and everybody's trying to take a shower, everybody's taking a shower, and then you have no water pressure. Well, that's what these are for, because it stores all this water so that when everybody's using the water at the same time, everybody still has that water pressure. And then when you go off to school or whatever, it fills itself back up. The water tower, yeah.
Where do you get the water from?
From the water plant. Like it's getting water from the water plant.
What is it? A long hose that goes to the water plant.
You can call it a hose, but it's more like a pipe. But yeah. I mean, it's the same idea. All right, and so that's basically what a capacitor does. The difference between a capacitor and a battery is that a capacitor can dump all of the water in a fraction of a second, whereas a battery has to take a long time to disperse all of that charge. Okay, so a capacitor can go from 100 to 0 in a matter of a fraction of a second and dump all of the charge. However, a battery has to take a long time to get rid of all of the charge.
Imagine a car going from 0 to 100 in a fraction of a second.
Mm-hmm.
That would be terrible.
We'll be there. We're almost there. It's like those high-powered 300-mile-an-hour trains or whatever.
What's it called?
Bullet trains or superconductor trains, whatever they are. Yep.
They have like the ones that like a magnetic train.
They're supposed to make one from Houston to Dallas, but I haven't heard anything about that recently. So, okay. So I'm supposed to kind of go over this. How does a flash and a camera work? Because it's the same idea. So you ever get one of those disposable cameras? Okay. Whenever you after you take a picture and it flashes, you'll hear this little humming noise. It goes, and it's ready to go. Or for those of y'all that have ever watched like television shows, like ER shows or whatever, and they use the paddles, you'll hear it charge up before they use the paddles on a person. It's the same idea. It's a big capacitor. It's charging up, and then it's going to disperse all of that electricity at one time. It's the same basic principle. It's also the same basic. Well, it's the same thing as a taser. Yes, exactly. I think they call them IEDs or something like that. So it's actually interesting. Yeah, but that's basically what it does. It's a big capacitor that's charging up and then shooting a bunch of voltage. You were an IED. Yes. Okay, so what do capacitors look like? Here are a bunch of different capacitors. I don't need you to write them down, but that's what they look like. Okay, here are some more capacitors in case you were looking for more. These are just showing you the measurements of those particular capacitors. Some of these are surface mounts. You can see the surface mounts over here, and then you've got some different ones, coaxial and disc. All right, here's some more capacitors. All right, and now we get to the ones that you actually need to draw. Okay, so you have the ceramic disc capacitor, and this is your symbol for a ceramic disc capacitor. You have your electrolytic capacitor, and this is your symbol for that. You have your monolithic ceramic capacitors, and then you have your electrolytic capacitors again. These are radial that have two legs on the same side, and then you have axial that have legs on either side. Yeah. Kind of look like Advil. Yeah. Yes. Or I should say generic ibuprofen. I don't know.
I feel like one day I'm gonna take Advil one day and like take this instead. It sometimes it doesn't have to look like. I can see it laying around like a model.
That's weird. But don't take them. Don't do it. All right, so that's those are the different types. Make sure you get the symbols, and you can see that these have a plus sign, which means that they are going to only allow the current to flow in a specific direction. So that's important to know. Which, if you did your lab, the last lab, you should have seen that resistors do not allow that, but LEDs don't do. Like resistors allow that current to flow either way, and LEDs only allow it in one specific way. You pop what? Yeah, and don't connect your LEDs up without a resistor. Don't do it. That was pretty weird. I've never seen one do that before. I've seen them smoke, I've seen them burn out, but I've seen them get real hot, but I've never seen them explode like that.
My thing is hot when I put the LED on it.
Yeah. Okay, so everybody should have all this. We're going to move forward. Some more different types of capacitors. You have your surface mount tantalum. They look like this, and then your surface mount ceramic. Ceramic capacitors do not have a direction, but the tantalums do. Okay, you can kind of see the size comparison to the rest of them. They're very small. But so ceramics do not have a direction, but the tantalums do. All right.
You done?
Ooh, we're done with that. Here we go, moving forward.
Oh, no, wait, hold on.
What do you mean?
Hold.
What? Some of this we're going to be skipping though.
I'm on the last one.
What time does class end?
Yeah.
We got time.
Okay.
All right, moving forward. This is just an explanation of how how the electrons are moving, how current works. Okay, so we've already kind of talked about this. The electron hole is what we're going to be dealing with right now. Positive ion attracts negative electrons. Okay, that's why electricity flows negative to positive. Okay, so this particular part you may want to go. No, maybe not, because I think this is still part of capacitance. So, positive ion attracts the negative electrons, right? Y'all understand that? It's like the proton attracting the electron because it has a positive charge. Okay, so when an electron moves from its valence ring, it's leaving a hole there. It's jumping from one atom to the next, right? And when it jumps to the next one, it's leaving a hole. So what happens when there's a hole? What's it going to fill up with? An electron from where? From the atom sitting next to it, right? Exactly. So that's kind of what it's going to do. So the negative electron tries to fill the void that's been made from the electron that jumped. So it's going to try to fill another hole. Yes. In a sense, they're saying that the hole's moving, but actually the hole is moving because it's being filled by another electron, and that electron is leaving a hole behind. So that's basically what it's doing. Okay, so this is where I'm supposed to show you a demonstration or have everybody do a demonstration, and but we're not going to do that because we can't hold hands at home. So that's not really what we're going to do. I'm just going to kind of explain it and hope that works. Okay, but that's what's happening right now. Electrons are jumping from one atom and going to the hole that's been created from the last electron that jumped, and creating a hole where it left. And then that's basically why things are happening. So we were supposed to make a demonstration, but we're not going to. We're just going to pretend. Okay? Pretend. We can pretend. They're in kindergarten. It'll be okay. All right. So this is our power source. Imagine that you have a person standing here, 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 here. Every little circle, gray circle is somebody. Okay? So what's happening? See if this moves on its own. So you have an electron here, and then you have a hole. So the electron is going to try to jump to this hole, and then the electron that was here would jump to the hole that was here, and then this electron would jump to that hole, and then the electron that was here would jump to that hole. Yeah. So then it's going to try to keep, and it's going to keep going until it gets back to the positive side. Oh. Oh. Oh, see? Oh, see, and this here is your current flow. Your electrons are moving. So now you have voltage, you have current. That's electricity. Whoa. And so that's how it works. So these are all different atoms. And it's jumping from one atom to the next, leaving a hole. And then the next atom next to it's going to have an electron that jumps. And so on and so on and so on. All right. Now, we're going to throw something in here. Okay, we're going to put a big old gap between these two atoms. Okay, which means there's a big gap that it has to get across in order to get to the next one. So what's going to happen is all of these electrons are going to be building up over here in front of the gap. And all of these holes are going to be built up over here on the other side. Okay, so you have all these electrons trying to get across, but the gap is too large, so it has all these holes waiting for all these electrons to jump.
So what happens if I charge it through the gap?
This is how a capacitor works. So this is what's happening. The capacitor is holding all of these electrons on one side, and then there's all these shortages on the other side. So this is what a capacitor does. Okay, you have the one side, you have two different conductors, one here and one here. And they're separated by something called dielectric. Okay, and we're going to go over the materials that you can use for dielectric, but that's basically what you have. You have one conductor here, and then you have a dielectric in between. I would write that down because that's how a capacitor is designed. That's what they are. You can write the picture if you want. You want to draw that picture? You can if you want. The next picture might actually help you out better. So I don't know if I should move forward or not. But we'll move forward because it's kind of the same thing. So this picture right here is better representation of what's happening. Okay, so you have this conductor up here where all these electrons are sitting, waiting to jump across to get to this other conductor down here. And then you have a material in between these two plates that's keeping those electrons from being able to just jump when they feel like it. And that material can be all kinds of different things. We'll talk about the different types of materials in a second. But something's going to go in between there that's going to keep that from happening. Down here, this is a simple made capacitor. And what this is there's a metal plate, and then there's paper, and then there's a metal plate, and then there's paper. And basically, you wind that all up, and the electrons are all going to be sitting on this metal plate right here, and they're going to want to jump to this metal plate, but they've got to get through the paper. And that paper is going to be your dielectric. Okay, so it has to be enough electrons or a big enough push to make it get through that dielectric. Does that make sense? Okay, and that's kind of what. So this is what it would look like if you looked at it from the front, kind of like a Swiss cake roll. Y'all have Swiss cake rolls? Those are so good. If you haven't had a Swiss cake roll, you should go try one. Pretty good stuff. In Walmart, they're Little Debbie snacks.
Oh, yeah.
They're called Swiss cake rolls. They're so good. Not as good as oatmeal cream pies, though. All right. So the different types of dielectric material that you can have, rubber, oil, paper, formica or mica, glass, ceramic, just kind of depends on the material that you're using or how easy do you want that capacitor to discharge or not. You can also use air. Air is a big part of a big dielectric, which is basically just a big gap. Okay. Discharge, some of the factors that change the discharge or change how much charge it can handle, how much area of the plate that you have that's holding the electrons, how much room is there, the distance between the plates, the farther the distance, the higher the voltage has to be, and then what kind of material is separating those plates. That's important. So depending on what kind of dielectric you're using. But those are three different factors that can change how much capacitance your capacitor can handle.
We're not going to finish this.
What do you mean? We're almost done.
No, I just look at how many slides we got.
No, don't look at how many slides we got. Look at the quality of the slides, not the quantity.
Can we just do the star one, then stars? Like, there's like stars, you know.
I don't know.
Those are important.
Let's just keep going. All right, we'll get it done. All right, so the mad dog face is the next part. This is another example of what's happening. Here's your wire, and you have a mad dog face off, I guess. Negative, positive, and you got a gap, right? So here you have a small amount of area that can hold electrons and can jump across. If you put a capacitor plate in the middle of that, you have a whole lot of electrons sitting here waiting to jump across. So that would allow more current to flow whenever it's discharged. Okay, and then all of those electrons jump across at one time. So charging and discharging the capacitor, the way it would work, basically you would hook up a battery to the capacitor, and then that will charge up your capacitor. So then all your electrons will sit here, and you'll have all your holes sitting here waiting. And then to discharge, you would connect it to a load of some sort, and then connect it, and then all the electrons would go across. Okay? And that's how it works. That's how you would discharge. One of the things you have to be real careful about with capacitors is that they will hold a charge for a very long time. So if you find like an old TV, don't touch it, or an old refrigerator, things like that, they have these massive capacitors in them. And people die because they go mess with these tube TVs that have this humongous capacitor. And what I mean by humongous, it's like 4 or 5 inches round, that sit on the back of these TVs. If you go and find an old TV, like if you maybe your grandparents have one or something, and you ever touch the screen and you get a static shock, that TV's got a massive capacitor in it, yeah, and sometimes if you put your arm next to it, you'll actually feel your hair pull like off of your arm. You know what I'm talking about? Yeah, that is because it has this massive capacitor in the back, and it's basically you're feeling the electric field coming off that capacitor going through your arm, like, and so you don't want to touch that, because if it discharges into you, it's not going to be pretty. You don't want that. That's why you have special tools to discharge TVs, and they call it degaussing and things like that, where they take this big wand and they kind of run it around the TV, and it discharges all the electricity. Okay, you don't want to mess with any of that. Refrigerators have them too, so usually they're underneath the refrigerator. Don't touch that stuff.
Man, thank you.
Okay, anyway, so lesson learned, don't ever touch that stuff. Basically, lightning is a huge capacitor. But yes, because the clouds are all holding all these electrons. And what are they trying to do? They're trying to jump, right? They're trying to jump across. That's what lightning is. Once there's enough charge, lightning will shoot across and hit something, usually some sort of tower, some other kind of conductor. And that's what lightning is. So it's jumping across that gap. The dielectric is all the air. That's how that's working. Okay, but basically it's a malfunctioning capacitor is what it's saying, because it's going off. The dielectric didn't hold up to the charge, so the charge got too large, and it shot across when we didn't want it to. All right. So how big is big? We need this. The Coulomb. This is the standard of electric charge, named after Charles Augustin de Coulomb. I imagine that's French since it has de, but I guess it could be Spanish. 1 Coulomb is the amount of electric charge transported by a current of 1 ampere in 1 second. So these are numbers and facts that we need to have in our notebook. Probably not going to use them in this particular class, but we need to have them. Here is the charge, the electrical charge in 1 Coulomb. 6.241506 times 10 to the 18 electrons. Those 3 things you need. We already have this. But here's your equations and everything. We don't really use this very much, but just so you have it. No, still write it down, because we might, I don't remember if I put it on the test or not. So write it down. But we just don't use it after this.
I'll write down the equation. That's all right.
Okay, so farads is equal to the capacitance over the voltage. Your capacitance is your amperes times seconds over volts.
What does C stand for?
What? C is capacitance.
What's the smallest?
Actually, this is a capital C, so this is your Coulomb, actually, I think. I don't know why it's doing that. No, that's right. Yeah, it's okay. We don't use this, but like one time. And then we move on. This is going to be something you'd go into more detail if you took the second electronics class. It kind of. It's not DE anymore. It's just E. It's no D. It's not digital anymore. It's analog. Yeah, the analog electronics class is called AC/DC. Yeah. Yeah, but I don't even know that they'll offer it anymore. I'm not sure if they're still not. We have a few people that take it, but it's not like a common class at the ATC anymore. So, or the amount of capacitance that requires 1 second for 1 ampere of charge to gain or to change the voltage by 1 volt. It's very complicated. Not really. It's just harder to understand at where you guys are at right now. Just probably why we don't really focus on it in class. All right. So 1 farad equals the amount of capacitance that requires 1 second for 1 ampere flow of charge to change the voltage by 1 volt. This is what they just said, so you don't need to rewrite that. This is just an example, though. Okay. So a standard alkaline AA battery holds about 2.5 amp hours. That means that a AA battery can produce 2.8 amps for 1 hour at 1.5 volts. Right. If you're pulling 2.8 amps for 1 hour, that is a lot. 2.8 amps is a lot. Most things we don't even want to deal with close to that. Okay. So there are 3,600 seconds in 1 hour. So the way that they're going to do this, to store 1 AAA battery's energy in a capacitor, you would need this 6,720 farads. So they used that equation that we had in the last, where we had our seconds and our amperage divided by our voltage to get our capacitance. And that's 6,720 farads, which is ridiculous because you can't really have something like that. So it's impractical to use capacitors to store a significant amount of power unless you do it at high voltage. So at 1.5 volts, that would take a massive capacitor and a very long time to charge that capacitor. So that's why we don't use that. That's why we use batteries instead of capacitors. Okay, so how do you read the capacitor's value? It's very similar to a resistor. All right. For electrolytic capacitors, they're going to give you the value written right on the side. So you don't even have to try to figure it out. They'll tell you, oh, it's 0.47 microfarads, and that's how you know. Okay. The ones that are going to be a little bit more difficult to read are going to be your disk capacitors. And they are going to give you values based on the numbers and letters that they have. So these codes with these letters over here, you're going to want to write down. I know, this is the long slide. Okay, but basically you have your first digit, your second digit, your number of zeros, just like the capacitor or the resistor. And then you have your letter, which is your tolerance. And there's a lot of different tolerances to go through. So, but you can see they skip some. So like there's no E, there's no I, things like that. So they skip a bunch of letters. Okay. If it's a disk capacitor like this, that looks like the ibuprofen, okay, this is always measured in picofarads. So it's going to give you these numbers, but it's not going to tell you the unit because it's always measured in picofarads. Pico, which is times 10 to the negative 9. Okay. Negative 9, is that right? No, negative 12. Okay, so this would be 472 and then 2 zeros, so 4,700 picofarads. With K is their tolerance, which is 10% plus or minus 10%. Okay. It's going to be fun. Okay, I'm going to move to the next slide. I know that you guys haven't written down the chart. I'm going to go to the next slide because the chart's on the next slide as well. All right. And so that we can kind of do some examples while you're writing your chart down. Okay, so to determine the value of this capacitor, you would write down, you would find your values. You have a 3, which is your first digit. 3 is your second digit. And then you have 1, which is the number of zeros. So that's 330. And then remember, we're doing picofarads. Okay, and then we have the letter J. So we come over here to our chart, plus or minus 5%. Okay, and that's how simple it is. It's not that difficult. It's not any more difficult than the resistor values, with the exception of the tolerance letters and having to know that. And unfortunately, I don't have a cool mnemonic to tell you how to remember all of the codes. But for the most part, I think they give it to you on the test, so you'll probably be given it for your final exam, so you don't have to memorize those. All right, and the next one also has a chart, so I'm going to go ahead to the next one too. Okay, so this one would be a 1, a 0, and then a 3 zeros. So then you'd have 3 zeros after it. Okay, and then again, picofarads. Then you have the letter K, which we've already done, which is plus or minus 10%. Easy, right?
No.
What do you mean no? It's the same thing as the resistors. Only you don't have to worry about colors with this one. It gives you the numbers. All right, so 10,000 picofarads. All right, so then you guys might still have some stuff to do, but we're basically done with the PowerPoint, because the remaining of this PowerPoint is teaching you how to make a capacitor, which we're not going to do. So this would be the end of this particular PowerPoint, kind of explaining the resistors and the capacitors and all that. Hopefully you guys understand how the voltage works, how capacitors hold a charge, and how they discharge all their current. Make sense? All right. So that's it. I'm going to go over, this is just common parts. You can look at that. If you'd like to, you can print this off and put it in your notebook if you'd like. Since you're already copying down your chart, you may not really need that. So, no, it's the same thing you've already done. You don't need to rewrite it. I am, however, going to stop recording.